I am an instructioner. This is the story of how I work. I live inside the memory at an address that marks my place. I'm not a word, I'm not a story, just a pattern of zeros and ones. Someone has to come and fetch me. Someone has to decode what I say. Someone has to execute me so I can become action and come alive. At the heart of the machine there's a sequence. 3 words, always the same. Fetch, decode, execute. Fetch, decode, execute. It's the beating of the processor that never stops its spin. Fetch, decode, execute, and start again. First someone has to know where I am. That someone has a name. Program counter is his name. He holds my address in the machine. Doesn't hold data, doesn't hold a value, holds the place where I am found. The control looks at that number and goes to fetch me from memory. My bits enter the instruction register, ready for the machine to read. But the counter points to the instruction. Where the data lives, that's for me to say. The counter points to the next instruction. That's the only place it needs to know. The data lives in another address, and I'm the one who says just so. Don't confuse the place I'm resting with the place of what I'll use. One is the finger pointing to the recipe, the other is what will go into the pot. Now the machine must understand my request. That's called decoding. Fetch, decode, execute. Fetch, decode, execute. It's the beating of the processor that never stops its spin. Fetch, decode, execute, and start again. I was only zeros and ones in memory. Now the control comes to read me clear. Opcode is the name of the part that tells which operation will be performed. Logic circuits interpret me. Every field has a purpose of its own, and the signals start to travel so each piece knows what to try. Decoded now, it's finally my turn, but the one who works is not me. If I'm an add, the values go to dialu, and it calculates what I've told it to do. If I'm load, a value leaves the memory to the register that I point to. If I'm store, the value makes the journey back from the register to memory. It flies, I only say what has to happen. The one who does the work's the machine, not I. And all of this happens at the right time. There's a clock inside the machine. A clock beats inside the processor, marking when each thing will turn. Every pulse the circuits move forward, registers capture what arrives. But one pulse does not complete me. I may need several to get through. One tick is not one whole instruction. Don't confuse the step with the whole run. And don't think the earliest machines had a slow and lazy clock. The Manchester baby back in 48 was already beating near 100,000 strong. The EDSAC just 1 year later was nearing 500,000 too. It wasn't the beat itself that was slow. The beat already ran this fast. It was the work each step could carry that was too little for the task. But there's one instruction that changes everything. The branch. I can be the conditional branch. I say, if it's 0, jump straight to 100. If it's not 0, then keep going forward. Continue along the path that waits. The control makes the counter point to another address instead. And the machine that walked in a straight line now chooses the path that I have led. And that's why it repeats, and that's why it decides. Without a branch, the machine walks in a straight line, does the same thing over till it's through. With a branch, it turns back, it repeats itself. It changes with whatever the result may be. Loop, condition, another routine. All of them are born from this same root. Changing the number in the counter is what makes the machine able to decide. Now watch it all working together. Registers hold on to the values. The ALU calculates each result. Memory holds data and instructions. Control commands each moment as it should. Logic gates decode me piece by piece. The clock keeps a steady, constant beat. Each part does its own job, and none does the other's job. Fetch, decode, stops its spin. Fetch, decode, execute, and start again. First, someone has to know where I am. That someone has a name. Manchester baby back in '48 proved that a program could live inside the store and be run by the machine itself alone. That was the principle it showed, but its pieces on the inside were arranged a different way. What I sang was just the pathway that kept forming through the years, day by day. And now a new question rises: how to fit a machine like this one inside a chip the size of a fingernail? What kind of transistor could lead us to billions of parts in one small place? This is the story coming next now, in the song that will carry on. The transistor that nobody wanted, that made the chip exist and live on. The machine knew how to calculate, but it still filled an entire room. The question remained. I lived inside enormous rooms made of tubes, wires, and heat. Every piece assembled one by human hands with endless work. The bipolar transistor came and made things better. Smaller than a tube, more reliable too. But putting thousands on a single chip was still a problem no one could contain. It wasn't a weakness of the bipolar transistor. It was the difficulty of putting many of them onto the same piece of silicon. Isolating each one on the same crystal took space, it took great skill. The more they tried to bring together, the harder it became to make them work. And there was an even older idea to control current with an electric field without injecting current into the control. A simpler path, more efficient too. Lilienfeld had already patented the idea in the 1920s, but no one could make it work. Silicon had a problem at its surface. At the edge of the crystal, the structure broke apart. Incomplete bonds, trapped charges there. The electric field arrived, but could not control the channel that had to form. Shockley tried it in '45, but he could not get the result he sought. The surface of silicon held a secret that no one had discovered yet. With every limit we encountered, someone searched for a way through. With every question left unanswered, a new idea came into view. The story of learning is the story of never stopping. Mohammed Atalla was born in Port Said, Egypt in 1924. He joined Bell Labs in 1949. He discovered that a layer of silicon dioxide could passivate the surface, reducing the charge trapping states. The surface that caused the problem became part of the solution. A thin layer of silicon dioxide, grown on the crystal with great care, protected the surface, stabilized it, and acted as an insulator there. A metal electrode placed above the oxide applied the field without touching the silicon, and the conduction channel finally opened, controlled by the field. Simple and precise. Atalla and Kahng was born in Seoul, Korea in 1931. He arrived at Bell Labs in 1959. With Atalla, he turned the principle into a device. Two researchers from different worlds, one from Egypt, one from Korea, crossed oceans in the search for science and met inside the same idea. In November of 1959, the first MOSFET truly worked. Metal, oxide, and semiconductor in layers, a structure of remarkable simplicity. In June of 1960, they presented their work at the Carnegie Institute of Technology. The title was Field-Induced Surface Devices in Silicon and Silicon Dioxide. Bell Labs did not make it a priority. Atalla left and founded the Semiconductor Laboratory at Hewlett-Packard. Kahng stayed for another 29 years. The bipolar transistor did not lose, it followed its own path. speed and maturity were its strengths, but the MOSFET had a new advantage, one that grew as scaling demanded more. The smaller the transistor became, the better its scale inside the chip, and that property would change everything when density demanded more and more. In 1962, Hofstein and Hyman demonstrated a MOS-integrated circuit with 16 transistors. In 1963, Frank Wanless introduced CMOS. In 1964, a commercial MOS chip had 120 transistors. The number was growing, the chip was shrinking. Kahng died in 92 at 61, Atalla died in 2009 at 85. Neither received the Nobel that history might have given, but their invention is still very much alive. More than 13 sextillion MOSFETs have been made. It is the invention that multiplied beyond measure. The MOSFET did not create the microprocessor by itself, but it showed how more and more transistors could fit onto the same piece of silicon. And that opened the next question. How could we bring transistors controlling a loop inside a single chip the size of a fingernail? How could we put the whole cycle that I just said inside a chip that could fit beneath the fingertip? That question remained unanswered until 1971, when 4 engineers answered it at once. 2,300 MOSFETs on a chip that fit in the palm of a hand for the first time. In the song before this one, Kilby brought the parts together. Noise connected them all inside the chip, but no one said how. Kilby showed that parts could be born together, made on the very same piece of crystal. Noise laid down a metal trace, connecting it all. No wire, no solder needed. But a question remained unanswered, one that had followed me from the start. How do you draw what no eye can see, thousands of times, with no error, no false start? The answer wasn't born in a laboratory, it was born in a print shop, because a German playwright didn't have money to print his plays. In 1796, Sennefelder turned to a slab of limestone. He had no way to pay for printing, so it was in the stone he chose to rely. He saw that grease and water repel. Where there was grease, the ink would hold. Where there was water, the ink could not stay, and the drawing appeared without carving the stone. From the Greek lithos, stone, graphane, to writing on stone. And keep this principle, because it's the same one that made me. You don't remove material to create the image. You create a chemical difference, and the image appears from it. In 1822 in France, Niepce wanted light itself to draw. Bitumen of Judea on a polished plate, hard, and wherever the light struck raw. Where it didn't strike, the solvent washed clean, and what remained was the pattern the sun had made. Heliography, writing by the sun, no lens at all, the image formed by contact. 135 years later, this is how a transistor would be made. But first, there was a problem in the silicon. The oxide covered the whole surface and kept the impurities from passing through. Just opened precise little windows to decide right where each region grew. But the method was black wax by hand, spread by whoever had the patience to try. Fine for a drawing, rough and simple, but the circuit demanded something more precise. The more complex the device became, the more intricate the pattern had to be, and no human hand in the world could keep up. With every limit we encountered, someone searched for a way through. With every question left unanswered, a new idea came into view. The story of learning is the story of never stopping. In 1955 at Bell Labs, Jules Andrus and Walter Bond went looking for the technique in the printing industry. They brought what came from circuit boards, from the copper traces of radio and TV, photorealistic photoresist spread over the oxide, a mask on top to let the light pass free. Develop, etch with acid, strip away, and the window opened exactly right. Right where the pattern on the mask had said no human hand ever needed to touch the site. Around that same time, for a different reason, J. Lathrop and James Knoll needed a transistor small enough to fit inside a mortar shell. They used photoresist over germanium and turned the microscope around. Instead of making the small thing larger, they shrank the larger design down. And it was Lathrop who gave a name that stayed across the years and arrived right here. Photolithography, printing with light, that's how I learned to appear. Two teams, two institutions, two different problems. Both patents filed the very same year. Together, those ideas became the technique I needed. There was no computer drawing circuits, no automatic check along the way. The pattern was cut by hand with a blade on a red film, piece by piece, day by day. Where the red remained, no light could pass. Where it was cut away, the light broke through. And photography shrank it all down hundreds of times until the size was right. And each one of those rounds is a mask layer, layer upon layer, aligned with micrometer precision. Because a contact that misses its mark is a circuit that will not work. And here's the engine that no one saw, behind the count that Moore wrote down. Each generation printed finer lines, more parts could fit within the same area. It wasn't the law of physics, it was a craft, it was the light learning how to draw. 10 micrometers was already within reach, and someone still had to want to use it all. Now light knew how to print the invisible. What was missing was someone with a reason strong enough. The cycle already existed, the transistor too. The technique to draw me was already there. Thousands of parts on a single chip was possible now. Someone just had to dare. And the one who asked wasn't building a computer, but a calculator from across the sea. Busicom came to Intel in '69, and that's the story the next song will tell. In the song before this one, Light learned how to draw. Mask, photoresist, 10 micrometers of line. For the first time, it was possible to print the minuscule. I already knew how to calculate, that much was proven. Register, control, loop, clock, memory. The fetch, decode, execute cycle was already the beat of all this history. And lithography let me dream of thousands of parts in a single place. But dreaming wasn't enough, someone was still needed, with a reason strong enough to make me real. In 1969, a Japanese calculator maker came to Intel with a request. Intel was less than 2 years old. Busicom needed custom chips for every function of the calculator. Ted Hoff looked at the request and proposed the opposite. Instead of many chips, each with its own function, a few programmable general-purpose chips, behavior defined not by the wiring, but by the instructions stored inside. It was the architecture von Neumann had described 24 years before in 45. Now the question was whether it could fit inside a chip the size of a fingernail. Stan Miser worked with Hoff on the instruction set. Masatoshi Shima brought the real requirements of the calculator and the logic of the application. Busicom chose the proposal. Shima went back to Japan, and for nearly a year, nothing happened. In April of '70, Shima returned to Intel and found the project standing still. No one had moved it forward since he left. The deadline was closing in and there was much to do. That same week, Federico Fagan arrived, coming from Fairchild with new technology. The self-aligned silicon gate that made the chip finally possible. Fagan had presented silicon gate technology at the IUDM in October of 1968. It allowed smaller, more reliable transistors and an internal connection technique that shrank the area of each one, Without it, Hoff's architecture would never have become silicon. With every limit we encounter, someone searched for a way through. With every question left unanswered, a new idea came into view. The story of learning is the story of never stopping. Fagan led the layout drawn by hand, and every line cut into the red film. In December of '70, the wafers arrived, and none of them worked. Something was wrong inside. One layer of the mask had been left out, and 30% of the gates hung open. New wafers came in January of '71, and the chip passed every single test. In March of 1971, the chip was delivered to Busicom. Intel then renegotiated the contract, returned the $60,000 of the design fee, and received in exchange the right to sell the chip to any other customer. On the 15th of November '71, the announcement ran in electronic news, a new era of integrated electronics, a 4-bit CPU. That was the news. Hoff proposed the architecture that made me fit. Maser defined the instructions I would follow. Shima brought the requirements that made me real. Fagan brought the technology that made me exist. The word microprocessor wasn't in the announcement. The datasheet called the 4004 a 4-bit parallel CPU. The name came after the thing itself. None of them invented what I am alone. Each one gave the step the other one needed. The 4004 didn't put the computer on a chip, it put the CPU there, and that was enough. Program memory and data memory were separate chips of the same family, but a CPU on a single chip the size of a fingernail was a question truly answered for the very first time. The series that began with Pascal in 1642 has reached this point, and the answer didn't come from just one person. From 30 tons back in '48 to 12 square millimeters in '71, 23 years, and I fell into the palm of the hand of anyone who knew how to tell me what to do. Every generation solved a problem it found without knowing what would come in the next step. Every discovery opened a door that the next one walked through without asking permission. But one question was left unanswered. Before me, every calculator had transistors locked to a single task. Add, read a key, light up the display. Every task had its own fixed design. Now I have 1,807 and function of the calculator. Ted Hoff looked at the request and proposed the opposite. In the song before this one, I told you why I was made. Now I'll tell you what's inside me. And for that, I have to start from the smallest. A transistor has just 3 terminals: gate, source, and drain, nothing more than that. The gate controls where the current flows from source to drain or stays where it's at. In the P channel, the logic runs reverse. The low gate turns on, a high gate turns it off. The world turned upside down, but always consistent, and the whole chip follows that one rule it's got. 10 micrometers, the minimum line width. A strand of hair is 50 to 100 micrometers, 5 to 10 times thinner than a hair. 1,807 that switch, 427 that carry the load, 66 capacitive structures beside them, 2,300 devices in the whole. Not every transistor plays the same part. Each type has its own place in the plan, and all of it fits on a single chip, just 12 square millimeters in size. But to understand what I solve, you have to remember what came before me. Every calculator had fixed circuits back then. The adder was built only to add. The one reading keys could only read keys. The one lighting the display, that's all it had. Every function with its own arrangement, wired one way with no room to change. To build a different machine entirely, you had to design it all again from scratch. Every new function, a whole new circuit. Every new circuit, a whole new design. Every design, a cost nobody wanted to pay. With every limit we encountered, someone searched for a way through. With every question left unanswered, a new idea came into view. The story of learning is the story of never stopping. The way out that Hoff proposed was an inversion. Instead of etching the task into the metal, build a machine that knows how to obey, and put the task into a list of orders that the machine will fetch and carry away. The circuits stay just as specialized, each one still knowing its own design. What became flexible wasn't the part, it was the order each part falls in line. But careful, this is where the mistake lives. The program doesn't switch my transistors on directly. The order comes from memory outside. The chip arrives in 8 bits ready to be read. The control unit reads it and only then sends out the signals that open the path ahead. Program instruction, decoding it right. Control signal, open path, and the action takes flight. That's the chain of command running through me, and not one single link ever skips its turn, no. And inside me, there are 2 kinds of devices. Some are part of the network that operates, add, compare, decode, and mark the time. They're born wired to that single function, and there they stay for their whole lifetime. Others are part of a circuit that stores and holds a value that comes and goes. The network theory never changes either, only what they're holding shifts and nothing else, oh. And what they hold is electric charge. Charge leaks away, charge fades with time. That's why it must be refreshed in time. 16 registers of 4 bits each, and 4 more of 12 to hold an address in place. One of them counts where the next order sits. 3 of them hold the return path, just in case the cell doesn't know what it's holding on to, whether it's a number, a signal, or a place. It holds 1 bit and keeps it while it can. The program gives meaning to the value it holds. And there are 2 tables the program cannot reach, fixed in the mask, back at the factory. When I add up a decimal digit, it can pass 9 and lose its true worth. There's a table that fixes it for me, born already knowing what to do at birth. Another converts 1 of 4 into binary code for me to read. Nothing a program says can change what they hold. They were fixed by the mask when I was made. So here comes the question that opened this song. How many of my devices have a fixed destiny? All of them, without a single exception. No order ever changes how I'm wired inside. The program never redesigns my body, it only chooses the path and the sequence. I didn't turn the transistor into something programmable that never happened and it never will. I made programmable the sequence that a fixed network of parts can fulfill. And that's what sets me apart from the calculator before. In it, the task lived in the metal. In me, the task lives in the order. And the order can be changed. I started as a crystal that could amplify, became an inverter, a gate, a register in line, became a unit that calculates and that controls, became the cycle that fetches and executes in time. And now I live on 12 square millimeters with more than 2,000 parts in their place. 24 years since that very first crystal, and every single part still knows its place. 10 micrometers. 10 micrometers.